In today's lecture, we shall be learning about imaging science. Let's look at the objectives for today. At the end of this lecture, students will be able to distinguish between systematic and random errors. We will be able to explain the concepts of precision and accuracy. Students will also understand probability distributions like the normal and Poisson distributions. We will look at confidence intervals and confidence levels, and we will also look at two statistics tests, the student t-test and the chi-squared test. We will also look at the performance of imaging systems by learning about the modulation transfer function. We can look at also image or filtering operations, image characteristics like spatial resolution and temporal resolution. When it comes to imaging, we can say the most basic challenge of an imaging system may be reduced to a simple problem, that of detecting a signal against a background of noise. So, for example, in radiographic imaging, the choice of technique factors like kV, MA, and time will influence the signal and noise levels in the image. In film images, noise appears as statistical fluctuations, which we call visual noise. In digital systems, noise is the random variations in pixel values. Digital images are also affected by the choice of pixel size, grayscale, and acquisition time. Image appearance can also be changed by different functions based on statistical distributions. Image reconstruction algorithms also make use of statistical distribution functions. So it's important to have some basic knowledge of the role of statistical factors in imaging. In any kind of imaging system where a receptor is used, the goal is to faithfully display the actual object being detected by the imaging sensor. Imaging sensors may contain several sensing stages. Each stage may have some level of uncertainty and error in how it detects the object signal. We can get a better understanding by defining error. Error is the difference between measured and the true value of a variable being measured. There are two categories of error: determinate or systematic errors and indeterminate or random errors. We shall look at each on the next slide. Determinate errors result from factors such as inadequate experimental design, malfunctioning equipment, improper use of equipment, and incomplete correction for extraneous influences. For imaging systems, some examples of determinate errors include overexposure or underexposure of films in radiography, incorrect time gain compensation settings in ultrasound imaging, and in MRI, for example, a fall-off in surface score sensitivity will be considered a determinate error. Indeterminate errors are errors that cannot be reduced by eliminating or correcting extraneous factors. They are caused by fundamental uncertainties in the variables being measured and in the process of obtaining and displaying the measurements. In nuclear medicine, for example, the random nature of radioactive decay and the statistical uncertainties in detecting ionizing radiations gives rise to significant indeterminate errors. Here are some statistical concepts relevant for imaging. We will start with precision. The precision of a series of measurements describes the range or spread of the individual measurements from the average value of the series. Precision improves as the influence of indeterminate errors is reduced. Accuracy is how close one gets to a target value. You can improve the accuracy of experimental results by reducing the influence of both determinate and indeterminate errors. Indeterminate error implies the result of a measurement may be different if the measurement is repeated. Bias occurs when determinate errors contribute to reduction in accuracy of a set of measurements. We shall now introduce the concept of a probability distribution. A probability distribution is a neat way to represent collected data. In order to create a probability distribution, we first construct a histogram of the number of observations for each measurement. By plotting the histogram as a fraction or frequency of times that each measurement is observed, we can model a probability distribution. This distribution can be used to obtain the probability of a specific value being measured if the experiment is repeated. For our purposes, understanding and analysis of probability distributions is important for the development of image processing algorithms. For example, algorithms that involve any kind of expectation maximization are inherently based on statistical models like the Poisson distribution. Examples of expectation maximization algorithms are maximum likelihood expectation maximization or ordered subset expectation maximization. These types of algorithms are used in PET, SPECT, and CT imaging for iterative reconstruction. We shall be learning about two main probability distributions, the Poisson and Gaussian distributions. The solid curve on this slide is the Poisson distribution curve. It describes what is called a Poisson process. A Poisson process is a model of a series of discrete events where the average time between events is known, but the exact timing of events is unknown. The occurrence of radioactive decay, which is the detection of counts of a radioactive sample, follows the Poisson probability distribution. The second broken line is the Gaussian distribution. If a large number of counts is accumulated for a radioactive sample, then the Poisson distribution curve is closely approximated by a Gaussian distribution curve. We can understand the Poisson distribution by thinking of it as a binomial distribution with a large sample size that is approaching infinity. The Poisson distribution can be composed of discrete or continuous data. As I mentioned a few moments ago, a large amount of data is required to construct the distribution. It applies to events in which the likelihood of a particular result is small. Also, the chance of any particular event is independent of previous events. This is in general true of the statistics of random events. Let's look next at the Gaussian distribution. The Gaussian distribution is also called the normal distribution. It is a continuous probability distribution. A Gaussian distribution is a bell-shaped distribution parameterized by two values, the mean of a set of measurements and the standard deviation of the measurements. The distribution is symmetrical with both tails extending to infinity. If we think of it as a probability distribution, then we can say the likelihood of occurrence of a value depends on its distance from the mean value. An application of the Gaussian function is its use as a filter in image processing. Gaussian filters are used for Gaussian smoothing or image processing to reduce image noise, but this also reduces detail. Let's now look at the parameterization of statistical distributions on this slide. In statistics, a parameter is any measured quantity of a data set that summarizes or describes an aspect of the data set. On this slide, we can describe any data that is described by a Gaussian or Poisson function by parameters like the mean, median, and mode. I have a table here to help us with defining these parameters. Mean is the sum of values divided by the total number of values. When values are placed in order of magnitude, the median is the middle or center value. Half of the values are greater than the median and half are less. On this table shown, because there is an odd number of values, the median is an actual data value. Median is also known as the 50th percentile. When data in the table are placed in order of frequency of occurrences, the mode is the most frequently occurring value or most common value. Another important statistical parameter is the standard deviation. The standard deviation for a series of measurements is a way to describe the precision or reproducibility of the measurements. The formula for standard deviation is shown here. Confidence interval is an estimate calculated from the data. It gives a range of values for a parameter such as the mean. The confidence level is a probability that the confidence interval will contain the true mean parameter. Typically, the confidence level is chosen before examining the data. Confidence levels are usually 95%, but you can also have 90% or 99%. So let's see how these two are tied together. If, for example, your parameter is the mean, then you would state the mean at a 95% confidence level at 95% confidence interval. To wrap up basic statistics, let's look at two statistical tests. The first test is Student's t-test. This test was first published in 1908 by William Gossett of the Guinness Brewing Company. Because he used the pseudonym Student in the publication, the test became known as Student's t-test. This test checks significance of the differences between two measurements or sets of measurements. If after taking two sets of measurements of, say, the activity from a radionuclide, and you get two numbers having different means and standard deviations, the question is whether the differences between these two measurements is significant. To test this, you would first calculate a t-value. A small t-score or t-value means the differences are due to random variations. A large t-score means the differences are significant. After calculating a t-value, you would use the table shown here to get a p-value associated with the calculated t-value. P is the probability that the difference is attributable to random variations in the measurement. 1 minus P is the probability that the differences between the measurements are significant. Low P values means differences are significant. Another test is the chi-squared test. This is used to determine the goodness of fit of measured data to a probability distribution function. It allows us to check that a data set is based on random phenomena. Remember that random phenomena like radioactive decay is described by a Poisson distribution function. So if the data fits a Poisson distribution, you can say it is based on random phenomena. If it does not fit a Poisson distribution, then it is not based on random phenomena. So far, we have seen a lot of statistics. Let's now look at some properties of images. At this point, we know our images are formed by X-ray photons. We also know X-ray photons may cause harmful effects on tissues. This means we must use as few photons as possible to form the best image. The best image implies an image that can show spatial or temporal details. Spatial details in an image are affected by signal levels and noise levels. Temporal details are affected by frequency information. So the trade-offs among spatial or temporal details and other variables are dealt with continuously in diagnostic imaging. To tie it to statistical distributions, the signal levels are called mean and noise levels are called standard deviations. Let's start by looking at the spatial information in images. Spatial information is characterized by spatial resolution. Spatial resolution is a way to describe the detail in an image. It is also the ability to separate two objects close to each other. Spatial resolution is affected by the imaging system. In digital detectors, the pixel size plays a role, although it is not the limiting factor or only factor. In functional MRI, spatial resolution means the ability to locate a specific foci of activation with millimeter precision. Let's learn about how spatial information is characterized and analyzed in an imaging system. Let's say that we want to check how an imaging system reproduces a point in 2 dimensions, meaning we want to see how much blurring is introduced. We can use a point stimulus to represent the point. The left figure shows the stimulus. If we had an ideal detector, the stimulus would look like the left image. On a real detector, it appears diffuse or spread out with a reduced peak magnitude as shown on the right image. The image of the stimulus is analyzed to get a point spread function. This kind of stimulus is used to analyze the amount of blurring introduced by an imaging system. We can look at another application on the next slide. On this slide, another application of the point spread function is the ability to tell if the imaging system is stationary or moving. You can see from this slide the moving platform on the bottom right has point spread functions that are skewed or tilted. This type of analysis is used with radiation badges. Suppose a badge reading shows an extraordinarily high reading. Part of the analysis done will be to determine if the badge was being worn when the large radiation reading was obtained. Imagine the badge having a metal mesh placed over the radiation sensor. If the badge was stationary, say it was left on a table in the X-ray room, it will show a point spread function like the top right image. If it was worn and the user was moving around, it will show an image of the point spread function as in the lower image. There are other spatial information descriptors. These are the edge spread functions and the line spread functions. Edge spread functions and line spread functions describe how the edge of an aperture or a line aperture affects an image of an object. Point spread functions, edge spread functions, and line spread functions are all related and all describe image blurring of a particular aperture like a point, an edge, or a line. We can describe what each aperture does to the image of an object by a mathematical process called convolution. We shall describe convolution on the next slide. On the previous slide, I mentioned that when you image an object with an aperture, the aperture affects the resulting image due to a convolution operation on the image. On this slide, I want to point out how a distribution function will be used in image processing to modify image appearance. This function is also called a filter. The process of applying a filter function to an image to affect its appearance is called convolution. The filter is called a convolution kernel. Convolution is like a multiplying operation. The formula is shown on this slide. This slide also shows several images processed with different convolution kernels. Image B is the original image that is convolved with several filters. Image A is a blurring operation on image B. That operation smooths the image but also reduces detail. This type of effect can be accomplished by a Gaussian filter. An edge enhancement filter of increasing magnitude has been applied to produce images C, D, and E. Edge enhancement can be accomplished by a Laplacian function as well as other filters. So far in the previous slides, we've been talking about operations in the spatial domain. Instead of using the spatial domain to characterize image information, we can use the frequency domain. In frequency space, small objects correspond to high frequencies and vice versa. We can analyze information in frequency space by using Fourier series. The Fourier series is a series of sine and cosine functions that can be used to describe many complicated periodic signals. Let's see next how we use Fourier series to transform spatial information to frequency information. To convert spatial or temporal signals into frequency domain, we use what is called a Fourier transform. We can use the inverse Fourier transform to convert the frequency information back to spatial or temporal information. The advantage of working in frequency space is that it is faster to perform operations like convolution on a computer. In diagnostic imaging systems, we encounter many convolution kernels used for image processing in the frequency space. Examples in CT are, for example, the B41 or bone kernel. In nuclear medicine, we may encounter Butterworth, Ramp, and Shep-Logan filters. These are all kernels that are used to convolve images to change the image appearance. There are additional applications of the Fourier transform. In MRI, it is used to convert time domain signals to spatial domain. In CT, it is used to filter images before back projection, resulting in a filtered back projection reconstruction algorithm. On the previous slides, we looked at spatial information and how it is characterized and how to convert it to the temporal domain. Let's now look at another image characteristic called contrast resolution. Contrast resolution is the ability to detect subtle grayscale changes and distinguish them from noise in the image. Contrast resolution is characterized by measurements related to signal-to-noise resolution in an image. It is important to point out that contrast resolution is not focused on small objects, but rather relates to small changes in signal intensity due to the presence of anatomical structures in the image. Contrast resolution is affected by the noise levels in an image, so we shall look at noise next. Let's start with grain noise. This type of noise is possible in screen film radiography, particularly in mammography if screen film is still used. Optical density in screen film systems is because of reduced silver grains. These silver grains may be visible to a mammography radiologist who uses a magnifying glass to scan for calcifications. So it is possible for these silver grains to be a source of noise. Another type of noise is electronic noise. In both digital and analog systems, the flow of electrons is what conveys a signal from point to point. Electron movements could be due to signal or due to noise. Electronic noise can originate from thermal noise, short noise, or other sources of noise. If electronic noise is part of the signal before amplification, then it will also be amplified. This will be a problem if the signal is low because the added noise can contribute appreciably to the noise in the image. In some imaging systems, electronic noise can be reduced by cooling the detector, electronic shielding, or designing noise reduction circuits. The next type of noise is structured noise. This is due to the pixelated structure of most detectors. Detectors are read out in parallel channels to reduce readout time. Each channel uses its own amplifier circuits. If amplifier circuits are not perfectly tuned with respect to each other, they will have different noise and gain characteristics, leading to structured or fixated pattern noise in images acquired using these detectors. Structured noise can be corrected by taking a gain image and an offset image. Gain image is image acquired in the absence of an object. Offset image is image with no radiation incident on the detector. These two images are calibrated images that can be used to correct structured noise by calculating what is called a flat field image. Flat field images are part of a calibration routine and are acquired either hourly, weekly, or monthly depending on the imaging system. Another type of noise is anatomical. This is a pattern that is present due to patient anatomy. For example, in abdominal angiography, where the vascular system is of interest, sources of contrast like bowel gas or the spine may be present. Using digital subtraction angiography, images are acquired before and after the injection of contrast agents. These images are subtracted, revealing only the vascular anatomy of interest. In chest radiography, where the ribs are a source of anatomical noise, using dual energy subtraction techniques, the ribs and other bone can be subtracted, revealing only the soft tissue contrast in the image. The advantage of imaging modalities like CT and MRI is that they avoid anatomical noise because they eliminate overlapping anatomical structures. We looked at different sources of noise on the previous slides. All these types of noise can affect the spatial resolution of an image. This is because noise makes it difficult to see fine structures in an image. Noise is typically propagated or transferred through the imaging system from one stage to another. If the noise source is structured or periodic, we can understand how it is transferred from one imaging stage to another by studying the modulation transfer function. The modulation transfer function is the response of the imaging system to different spatial frequencies. On this slide, we can stimulate an imaging system with several input signals of different frequencies. We can see the output signals on the right of the top figure. These output frequencies represent the response of the system. The amplitude of the signals are reduced by the imaging system, as you can see. The high frequency signal is attenuated more than the lower frequencies. The loss in amplitude is the result of resolution losses in the system. Below is a plot of the modulation transfer function. The modulation transfer function shows the amplitude reduction as a function of spatial frequency. The plot is normalized to 1. You can think of the vertical scale as the contrast level associated with each periodic structure in the input. We will see next how to interpret the modulation transfer function curve. Suppose we measure the modulation transfer function for an imaging system and we obtain the curve shown on the right. If we agree that for this imaging system the limiting spatial resolution is the resolution at which the modulation transfer function is at 10%, then we can read the spatial resolution of the modulation transfer function curve. So in this figure, the limiting spatial resolution is 1.6 line pairs per millimeter at 10% of the modulation transfer function. Modulation transfer function is a useful measure of true or effective resolution because it considers the amount of blur and contrast over a range of spatial frequencies. The modulation transfer function can also be measured with a point, a line, or an edge aperture. These apertures are described by the point spread function, the line spread function, or the edge spread function. On this slide, I am going to introduce some imaging terms and get into more detail in a later lecture. The terms are contrast to noise ratio (CNR), signal to noise ratio (SNR), and detective quantum efficiency (DQE). Contrast to noise ratio is a good metric for describing the signal amplitude relative to ambient noise in an image. Signal to noise ratio is similar to contrast to noise ratio, except that the size and shape of the object is explicitly included in the computation of signal to noise ratio. Detective quantum efficiency is a description of the overall frequency-dependent signal to noise ratio performance of the imaging system. We have been learning about spatial resolution on the previous slides. Let's now look at temporal resolution. Temporal resolution is the ability to resolve fast-moving structures. It is the discrete resolution of a measurement with respect to time. Temporal resolution may be equated to the sampling period. High temporal resolution will mean a short sampling period, which means a high refresh rate when displaying images on a TV screen. In this context, we are referring to something like the pulse rate, which makes an image appear to move smoothly. For example, in a GI swallow study, if the motion appears choppy, an increase in pulse rate can produce a smooth motion. So high pulse rates in fluoroscopy imaging allows any motion to look smooth. Here is another view of temporal resolution. In this analog to digital conversion process, part of the process involves sampling an analog signal to convert it to a digital signal. An analog signal in the form of voltages are sampled and converted to digital signals containing zeros and ones. The digital signals are converted back to analog signals by a digital to analog converter. If a large number of samples are taken, the digital signal will produce an analog signal that looks closer to the actual analog signal. With few samples taken as shown in this figure, there is information loss. This lost information is not recovered when the signal is converted back to an analog signal. The temporal resolution is improved by reducing the sampling period so that more samples can be taken. Let's finish up with a few questions. First question: what test will be used to determine if the difference between two data sets is significant? Your choices are chi-squared test, student's t-test, MTF test, random noise test. The correct choice is student's t-test. Next question: what statistical test will show if a set of data is the result of random phenomena? Your choices are chi-squared test, student's t-test, MTF test, random noise test. The correct choice is chi-squared test. Next question. A chest radiograph is taken at a kV of 120, resulting in an image that reduces the influence of the rib cage, allowing the lung structures to be visible. This approach of using a high kV for a chest eliminates what kind of noise? Your choices are structured or periodic noise, electronic noise, grain noise, anatomic noise. The correct choice is anatomic noise. Next question. A technologist performing a radiograph of the knee selects a kernel that reduces noise by smoothing the image. This type of kernel also resulted in one of the following. First, no changes in the resolution. Second, decrease in blurring. Third, enhancement of the edge structures. Fourth, reduction in detail. The correct choice is reduction in detail. This is the last slide. Thank you for watching this presentation.